Hi, good evening. Okay, it's 6, so let's start. Welcome to week 3 of Data Science for Engineers problem solving session. I am your problem solving PA, Salati Pravanika, and I'm a PhD scholar from Indian Institute of Science. And I'm also a Prime Minister's Research Fellow. And yeah, so before we begin the session, I would like to say that this session is being recorded. And I'll give you like 3 to 5 minutes break after every half an hour and 10 minutes break after every 1 hour. And if you would like me to cover any more topics in the next sessions, you can always tell me in the chat box and I'll make a note of it. And be respectful during the session, and I will definitely not hesitate to remove anyone from the session in case if you are not being respectful to either towards me or any other fellow participant. Okay. And yeah. And today we'll be covering some of the important topics. Those are introduction to random variables and how they are characterized by probability measures. And please make a note. I won't write probability all the time. I'll just write it as PROP and a full stop. Okay, just take it as a shortcut. I mean, short form that I'm writing. And probability density functions as well. And how parameters of the density functions is estimated. So we call them as estimations, and also we'll cover hypothesis testing for decision making. Also, this is not a theory class. All the theory has been covered in the weekly materials. Okay, I hope all of you have gone through the video lectures on NPTEL, and I won't go too much into depth. I'll just tell you like what is exactly it is like a definition sort of, and then I'll directly jump into problems, and then I'll go to our code. Okay. So please don't expect too much of theoretical things from this session. Okay. I hope I'm clear. Yeah. So let's start. Quick recap. So we have something called as a phenomenon. Okay, phenomenon is basically like a situation. For example, if we are tossing a coin, so this example is going to come across your entire probability and probability, right? So So a phenomenon is a situation that is occurring. Okay, it can be a coin toss. So that is head out some outcome I'm going to get given a situation, right? So in every situation there are two types. We get two types of outcomes. So one has only single outcome, only one output, right? And another one is like you'll have multiple outputs but with some probability. So deterministic phenomena means only one outcome is going to be there for a given question. So if I ask you, what is your name? Your name is going to be just one, right? We don't give 10 different options to everybody, like until and unless your name is too long and you have to move names, right? And if I ask you, what is your height? You just give me one option, like I'm this 5 foot something, right? So that is called as deterministic. Just having one outcome and that has like a full probability. And another phenomena is stochastic, means it has multiple outcomes. So if I'm taking a dice, if I roll a dice, I might have 6 types of outputs, like 1, 2, 3, 4, 5, and 6. Right? Any one of the outputs I might get whenever I roll a dice. So that is called as a stochastic phenomenon. So today, most of the probability will be dealing only with stochastic phenomena type, because that is something having so many outcomes with different probability for each outcome, right? And yeah, apart from that, we have some sources of error in every phenomena. So one is model error, another one is measurement error, right? So in model error, it is basically from the error because we did not take something into consideration when we are calculating something, right? That is model error. And measurement error. We might be taking we are using some equipment to measure something, and that equipment is not precise enough, so they might give you measurement error, right? So that kind of an error. We have different types of phenomena. The first one is the random phenomena, and the other one is the continuous phenomena. All of this has been covered in the lecture series. So I would suggest you can go through that one in more depth. Okay. So there are some important terms that we'll use throughout. The first one is the sample set. So sample set is basically set of all the possible outcomes that we are going to get. So for example, again, I'll take a dice. If I roll the dice now, so what are the possible outcomes for me? 1, 2, 3, 4, 5, and 6. So these are all the outcomes. So this numbers from 1 to 6 is called as my sample set for a dice, right? So let's do it as an example. Consider this black line. So that's the question. So consider the experiment in which a coin is tossed repeatedly until a head comes up, right? So what do you think is the sample set for it? I'll wait for 2 minutes. You can type in the chat box. I'm not asking about uh, a probability or something like that. I'm asking what can be the possible outcomes. So if I'm taking just one coin and if I flip, it's either head or tail, right? So instead, now, yeah. So if I'm taking a coin and I'm tossing it until head comes up, um, okay, there are different possibilities for me here. Okay. I take a coin, I flipped it, and immediately I got head. So that is one kind of outcome, right? No, no. I'm just taking what you have told, like head, tail, and all of that. That is for two coins. Okay. So here I'm taking just one coin and I'm repeatedly tossing it until I get head, right? So as soon as I flip, if I get a head, that will be my outcome. So what if I flip for the first time and I get tails? Then I'm going to flip again. Then I might get a head. Okay. So that also did not happen. First time it was tail. Second time also it was tails. So I'm going to do it until I get head, right? So this is how the sample space here is. Okay. Is it clear or do you want me to explain it again? If anyone is not clear, it's okay. I can explain it. Okay. I hope the question there is clear. So you have to keep repeatedly tossing it until you get a head. Okay. Okay. So then we'll take something called as an event. So event is a small subset of the complete sample set. So in this case, maybe I'm saying I'm going to toss it 3 times and I'm just going to take only this small part here. Okay. I'm going to toss only 3 times and then I should be able to get a head. Then what is the sample space, right? So it is a small subset of this entire sample set that I have. Okay. So that is called as an event. Probability measure. This is something you guys already know. So this is the function that is, so we are going to assign this probability to some value, right? For example, if I'm taking the head and tail, the probability of getting a head is 50% and the probability of getting a tail is 50%, right? 50-50% chances I have. So this 50%, I can write it like this, and that is nothing but 1 by 2. So this 1 by 2 is nothing but the probability. Okay, probability of getting a head is equal to 1 by 2. Probability of getting a tail is equal to 1 by 2. So this is called as the probability measure. Okay. And the important conditions to note here is that probability is always greater than or equal to 0 and always less than or equal to 1. Okay. It is never greater than 0 and never less than 0. Okay. So that is for single probability. Now, if I'm this S here represents sample space. So the entire sample space is equal to 1. Okay. So now if I'm having both this head and tail as probabilities, if I add both of them, 1 by 2 plus 1 by 2 is equal to 1. So this 1 by 2 and 1 by 2 is nothing but the sample space, right? That is head plus tail. Okay. So that is nothing but 1. And I hope probability of sample space is equal to 1 is clear. And then let's come to some Venn diagrams. Okay. Now let us take an example. Okay. There are some people who likes dogs. There are some people who likes cats only. And in the population that I have taken, let maybe like 10 people I have taken, I have asked everyone, do you like cats or do you like dogs? Okay. Maybe some people have told that they like cats. Some people told they like dogs. But there are no people who told me that they like both dogs and cats. Then that set of people are called mutually exclusive, right? So they like some cats, they like dogs, but there are no common people in between. Okay, so those are called as mutually exclusive. And then if I'm taking independent events, so maybe in the same 10 people, I'm asking again, do you like dogs? Do you like cats? Maybe four told I like dogs, four told I like cats. Then two people told me I like both dogs and cats. So there is some overlap between both the likings. So those are called as independent events. Okay. So, so this mutually exclusive, if I'm going to take the union between A and B, then it is going to be nothing but addition of A and addition of B. Am I right or wrong? If I'm taking the union between P of A and P of B, I mean the set of A and set of B, then it is nothing but the addition between A and B, right? Because we don't have any overlap in between here. Okay. So in case if we are taking an independent event, we have some overlap, right? So let us say now I'm a person who wants to know only who are the people who likes both dogs and cats. This part here, so I want to know who likes it. Then I can use this P of A intersection B is equal to P of A into P of B. So they don't have influence on each other and they are called as the independent event. And P of A into P of B is only for this, right? And this kind of a diagrams representing in circles the events are called as Venn diagram. Okay. So we'll go to the next one. So now, okay, if I'm having two or three, I'm able to count it and I'm fine with it. But what if I have I have to conduct an experiment for like 100 times or 150 times or 200 times? I can't keep counting it all the time, right? So instead, what I can do is I can write P of A is equal to NA by N. So NA is the number of times the specific. So let if A is some event, then N of A is the number of times that event has occurred. And N is the total number of times we have conducted that event or things like that. Okay. For example, uh, okay. Take an example of tossing two coins, right? So what will be my sample set? I might get two heads, and then I might get head and a tail, or I might get a tail and a head, or I might get both tails, right? So if I'm asking you, what is the probability of getting both heads? What what is the probability of getting both heads? then I might say only one time that is occurring. So 1 by, so we are getting total 4 outcomes, right? So the probability of P of H is 1 by 4. Like that, if this number keeps increasing uh, with respect to the frequency, then we can calculate the probability directly. Okay. So I would like you guys to use this particular formula here and try to answer this question. You can drop your answers in the chat box and I'll give you like 2 minutes. I'm so sorry, I was on mute the entire time. I'll just repeat it again. I'm really so sorry. I'm so sorry. I was on mute and I did not realize it. So I'll just start it again. Okay. So n is given as 500. Okay. Let's just write all the parameters down. Let us call this first. Let's go for the first one. It is given as n of 2 heads, that is denoted as NHH, is equal to 105, right? So P of H is equal to n of HH by n, which is equal to 105 by 500, which is equal to 0.21. huh? Sorry, yeah, 21. Okay. So the next one is we are having just one head, and that is given as 275. So P of H is equal to N of H by N, which is equal to 275 by 500, which is equal to 0.55, right? The next one is having no head, that is 120 times. So P of no head is equal to number of no head divided by total number of total number of times the coin is turned. 120 by 500, which is equal to 0.24, right? So these all are okay. Initially, we were saying there are some probability conditions, right? What is the first one? First one is probability always lies in between 0 and 1, and P of S is equal to 1, right? So now let us see. This is in between 0 and 1. This is in between 0 and 1, and this is also in between 0 and 1. So the condition 1 is fine. So let us check the condition 2. P of S is equal to 1, which means the sum of all probabilities should be equal to 1. So add all of this 0.25 plus 0.55 and 0.24. All of this will give you 1.00, which is equal to 1, right? I hope everyone is clear with this one part. Okay. And another two rules that I wanted to say in between this is that, so if I want to take complement of something, okay, if an event called A is occurring, but I want to know something complement of the event A, which is event A not occurring, then that is equal to 1 minus A, right? So this can be said like event A occurring plus event A not occurring, which is nothing but the sample set, and that is equal to 1, right? So A complement is equal to 1 minus A. No? Yeah. So for example, if this is A, all of this is A complement, right? The sum of A and this A complement is nothing but the sample space S. Okay. The second one is that if an event B is a subset of A, that is, if the whole thing is A and B is a subset of A, so B lies inside A, then the probability of A is greater than probability of B. Okay, that is the second rule. The third rule is that if you want to know the A union B, let us say this is A and this is B. This part is A intersection B, and the whole thing is A union B, right? So if I want to know the entire A union B, then what I have to do is P of A plus P of B minus P of A intersection B, right? So these are some of the key things that you have to remember. Okay. Uh, let us look at conditional probability. Okay. So the first and foremost condition in conditional probability, we should assume that A and B are not independent. Okay. That is, the outcome influence each other. That is, we want to know the probability of one, given that we know the occurrence of another one. Okay. So if I'm having two balls in a bag, let us say one is red and one is green. Okay. Now I have taken one ball out and I observed that it is red, then obviously the other one is going to be what? Green, right? So if I take it and I tell to the other person the same thing, now in my hand I have this one particular color. What will be the other color? Okay, so that is the condition that I'm telling, and I'm asking for an outcome of it. Okay, so that is called as a conditional probability. Okay, and it is given by this formula. A. So if I want to know A when B is given, then I have to, if I want to know A when I know B, okay, B is known in this formula and A is unknown. Okay, then the formula is P of A intersection B by P of B. So P here is the probability, and we all know that. And also, this is the main condition. P of B should always be greater than 0. We cannot have an infinite value here. So we cannot have this is 0. So that should always be greater than 0. Right? So let us try. Example, we'll try this problem out. So I'm having 6 red balls, 3 blue balls, and 1 green ball. Okay. So I'm saying the first ball is red. So what is my P of A? I want you guys to just type it in the chat box. P of A. A here is the first ball is red. Okay. So before we say what it is, we have to find the total number of balls. What are the total number of balls? 6 plus 3 is 9, 9 plus 1 is 10. So n is equal to 10, right? So I'm saying the first ball is red. So I have picked up only just one ball. So that is 1 divided by n. That is 10, right? So that is okay. Now let us find B. Okay, given that all the 10 balls are there, the second one is not green. Yeah. So you can do it in two ways. One is that okay, we have whatever green is there, you just close it off and we take the other numbers. So that is 6 plus 3, 9 divided by the total number. But instead, you can also do it like find the green, how many number of greens are there. So I'll get just one ball out of 10, right? I don't want green. So which is nothing but 1 minus P of greens. So that is equal to 1 minus 1 by 9. And that is 9 by 10. So alternative. This is just an alternative. Okay, alternatively, you can write it as this will also. Okay. Now, I want to know the P of. Okay, what is the P of A intersection B? So it's like a diagram. So this is A. Okay, that and this is B. A means red only, right? And B means no greens at all. I have an overlap here because the second part is not green, which means the other options are red and blue, right? There are some intersections for me. So those intersections are nothing but red colored balls, right? So P of A intersection B is equal to red balls divided by total number of balls, right? So 6 by 10. Okay. Now it is very easy to solve P of A intersection, sorry, if I want to know P of A given B equal to P of A intersection B divided by P of B. Okay, what is it? 6 by 10 divided by 9 by 10. It's 2 by 3. In case, So this is one type. In case I want to know P of B, P of A, why is it not 6 by 10? No, no. In P of A, we are just picking one ball, right? Oh, sorry, sorry. I'm so sorry. Yeah, that is actually 6. You're right. Yeah, that's it. No? I'm so sorry. You're right. It is 6 by 10. It is 6 by 10. Okay. Thank you so much for correcting me. Okay. I was thinking green and I was just like, I'm so sorry. Okay. So let's continue. So if I wanted to find P of A given B, then this is how I'll do. In case if I want to find P of B given A, it is equal to P of A intersection B divided by P of A. That is equal to 6 by 10 divided by 6 by 3 equal to 1. Okay. Okay. Uh, yeah. And then we have base formula. So this is base formula and derivations and all you can look up on the textbooks as well. And it is going to take a lot of time for then all of that. Okay. So I want you guys to solve this problem. So once you're done solving this problem, we can look at our code. Please solve this problem and we will look. So in this problem, we have 5 red balls, 3 green balls, and 2 balls are drawn at random. Find the probability that both are green. Um, okay, okay. So we'll see. So let us call this as B. Okay. So what exactly is this B? It's blue plus red, right? And what is A? Just red. Am I right? Uh, okay. Another person also got it or no? So now if I'm going to take the intersection between both of these, then it's going to be red, this whole red part, and the blue is a different part, right? So that is why P of A intersection B is equal to the same thing. Okay, please do the problem now. Guys, can you just write which probability are you talking about? Because is it like both greens? We are not going to combinations yet. simple ones. Okay. Okay, we'll do it. So let us say these are the two balls that I'm taking it out, right? So initially I'm having n is equal to 8. Let us say the first ball is green, then the probability is 3 by 8, right? Now I have taken it, so keep it aside. Now how many balls I'll have? 7 more will be remaining. Thinking that one green is already here, right? Then how many greens will be left? 2 greens. So total 7 balls. So this is going to be my 2 by 7. So if you remember in the beginning, we were multiplying P of A and P of B here. Here. P of A intersection B is equal to P of A into P of B. Right? So the same thing we will follow here. So the P of green is equal to 3 by 8 into 2 by 7. Okay? Simple. Okay. So shall we look at it? Yeah, that I did not say. Without replacement. So once I'm taking the ball out, then that's it. I'm not going to keep it back again. Okay. Uh, are you guys able to see? I'll clear everything. Okay. So yeah, at the end, I'll share all of this with you. So the questions, solutions, everything will be here. Yeah. So yeah, we know that P of A is equal to 3 by 8, right? You can just give the values here and you can just multiply the values and you will get it. Yeah, 3 by 8. So any questions on that? Okay. So next we are going to go to a very important topic. So that is random variables. Let me just share my screen again. Okay. So the next topic that we are going to look at is random variables. So random variables means the function that maps outcomes to numeric values. So it's like if I'm having head, if I'm having like 50% of the probability, then it's 1 by 2, and having tail as 1 by 2. So this is some real value, right? It's 0.5 and 0.5. Like that. If I'm having some different kinds of outputs, I might map it to like some value, some real values. So those are called as random variables. Okay. So these random variables are of two types. One is discrete, another one is continuous. So discrete are something that we are looking till now, like taking the number of walls and having some probability for each color and things like that. Okay. So if I'm looking at continuous, it is like it's going to be a continuous graph for me. For example, continuous number of heights. Okay. So these random variables, we will use something called as a probability distribution. Okay. So these are sometimes we have so many outcomes, right? For example, let us say I'm having like 1,000 colors in a bag. If and so many so many same colors might repeat so many times, so many colors, so many outputs. Then I can't keep on writing. Okay, P of red is this, P of green is this, like that. All colors I can't keep writing, right? So instead, what we do is to it's not possible to track everything. So instead, we use their probabilities. Okay. In such cases, we use a mathematic function to represent these outcomes. Okay. So those are called as probability distribution. For discrete, we have some kind of distribution. For continuous random variables, we have some kind of distribution function. Okay. So the ones which we use for discrete are called as probability mass function, PMF. And for continuous, we call as something called as PDF, that is probability density function. Okay. So probability distribution means to understand these random variables. So we should know the probability distribution. So it tells us what is the likelihood of each possible value or a range of values. Okay. You may not get a crisp of it here, but as we do, you will understand. Okay. So let's start with the easiest one, which is a discrete one. Discrete one is very easy. So that is like probability mass function. Okay, so that is a probability distribution that we use for this PM, right? So we assign some probability to every outcome in the sample space. We know that, right? So we have this head and tail, and we are assigning it to some values like 0 and 1. I'm just labeling it. Okay. Then I'm writing it in this probability form. So P of x equal to 0 is 0.5, P of x equal to 1 is 0.5. So this is used for discrete random variable. Hmm? And then, so this is the normal representations that we were seeing so far. So PMF is just the same. And when it goes to PDF, so as I was telling, it is a continuous value like this. So it keeps going. So keep we can't find each and every point, right? So instead, what we do is we take some intervals. For example, let us call this as A and this as B. If I want to know the probability that some value falling in between A and B, okay, maybe that value is somewhat here, right? So in between this interval, and I want this particular number to be in between this interval. So what is the probability? The probability will be the area covered under this curve. Okay, that is it. So here you can see. So the probability of having x in between A and B. Okay. So that is nothing but the area in between A and B. And we denote it in integrations. How many of you don't know integrations here? So full. Can you react to the poll? If you don't know integrations, please let me know now itself. Like, we don't need strong integration, just the basic. Okay. So I hope everyone knows integrations here. Right. Okay. So if I want this x to be in between a and b, then I will have the area that is covered in between the intervals a and b. Okay, that is okay by me. Then if I want to know the probability of just b, okay, actually b is supposed to be here and a is supposed to be here. Oh, sorry, I was just trying to. So, okay, if I want to know f of b, so what is the probability of? Oh, it's okay. Uh, I hope you know integration, sir. It's okay if you're not able to submit the vote. If you don't know integration, then just say yes. Sir. Okay, thanks. Ah, so if I want to know the probability of having B, then I will take the area that is covered up and until the point B. So that is, you can learn. So if I call this as B and this as A, minus infinity to plus infinity. If I want to know the probability of it lying in B, then I'll take all the area starting from minus infinity to B. Right? Here you can see it clearly. Okay. So this f of B is nothing but the cumulative density function. Okay, you are going to entirely take right from the beginning till the point B. Right? Okay. We'll try one PMS problem and one PDF problem. So you can try this example once. So I have given some hints as well. You'd like, if you'd like to use it. If not, amazing. The second one is not exactly a hint. It is just for you to remember. You can tell the k value if you figure it out. Take your time. I'll give you enough time for this. Done. K value. Okay. Anyone else? Yeah. So a quick question. Here we are having k square, no? Aren't we supposed to get two k values? Yeah. Then why haven't you guys considered it? Amazing. So yeah, let's do it. So here, the first thing is sum of all probabilities is equal to 1, right? So let us take all the values here, all these values. 0 plus k plus 2k plus 2k plus 3k plus k square plus 2k square plus 7k square plus k is equal to 1, right? So k plus 2k 3 plus 2 5 8 and 9. 9k plus 7 10k square is equal to 1. I can rewrite it as 10k square plus 9k minus 1 equal to 0. Splitting this 10k square plus 10k minus k minus 1 equal to 0. Taking 10k common here, k plus 1. Taking minus 1 common here, k plus 1 equal to 0. So it's 10 plus 1 into 10k minus 1 equal to 0. So we have two here, k plus 1 equal to 0 and 10k plus minus 1 equal to 0. So if I take this, k is equal to minus 1, and if I take this, k is equal to 1 by 10. We are not taking this one because we have our probability lying in between 0 and 1 only. Probability is always positive and less than 1. And we won't take this value. So instead, the k value is equal to 1 by 10 only. So amazing, Lavanya and Dishali, you guys are right. Okay. So, okay, the first part is done. The second part. Let's do the second part. Find the probability of if P of k less than or equal to 6. I'm also going to say. Actually, I don't exactly remember the answer, but we will do it. Okay. So P of x less than or equal to 6 is nothing but P of 0 plus P of 1 up and until P of 6, right? So totally I'm having only 7 in my sample space. So what I can rewrite it as P of x less than or equal to 6 is equal to 1 minus P of 7. Is it not right? P of 0 up and until P of 7, if we sum all of it, it is equal to 1, right? I need from P of 0 to P of 6. So can I write that value as 1 minus P of 7? Hmm. So I'll write it like that. 1 minus, so P of 7 is what here? K square minus K. Let us put this 1 by 10 value here. So let's write it as 0 0.1 minus 0 0.1. Sorry. 0.01 minus 0.1. 1 minus 0 0.1 is 0 0.9 minus 0 0.07. Right? That's 0 0.83. Okay. The first one is 0.83 until and unless I have made some calculation mistake. Okay. If I did a calculation mistake, I'm sorry beforehand. Okay, this is the first part. If we are going to take the second part, P of 3 less than x less than or equal to 6, which is equal to P of x is lying between 3 and 6, but it is not including 3, right? P of 4 plus P of 5 plus P of 6. What is P of 4? 3k plus 5 is k square plus 2k square. 3k plus 3k square. Okay, k is 0.1 and k square is 0.01. 3 into 0.11, 0.33. Okay, thank you for the confirmation. Um, so is this one clear? The second part of it? Okay. So if that is done, let's go to PDF. So if you guys want, you can take break also, or if you do you guys want to have it after this question? Anything is up to you. If you want, you can have some break, and then you can come back and do this one. It has been already an hour since we have started. You can take like 10 minutes break. We can start again at 7. Slides of video lectures, I don't think I can give them. I don't have it to give it to you as well. So it's basically you have to ask in the forum, and one of the course, like course TAs, they'll tell. I'm a TA for the problem solving session only, so I won't be able to answer that question. Okay. And the only way to talk to the other TA is through the forum. Okay, you can just drop a message in the forum again, and hopefully the TA replies. Okay, uh, shall we start? Let's start. Shall we resume? Shall I start or should I wait for 2 more minutes? Okay, let's start at 7:10. Thank you. Uh, do you guys want some time to work on this question or can we just continue? Okay, I'll just start by default. Thank you. Okay, so we have this function f of x, and at every point of time, it is having different output value. So from 0, if x is in between 0 and 1, it is represented by x. If it is between 1 and 2, it is 2 minus x. And if it is greater than 2, it is completely 0. Right? So now, what do I want? A is equal to 0.5 and B is equal to 1.5. Right? So f of 0.5 less than x less than, we'll just solve it. I don't remember the answers. Okay, 0.5 less than x less, sorry, x lies in between 0.5 and 1.5, right? So we can write it as this way. So f of x into dx. So now we have these intervals, right? So what we can do is starting from 0.5 to the next interval upper bound, that is 1, f of x into dx plus from 1, the other thing is 1 to 2, but I want it only till 1.5, right? So 1 to 1.5 f of x into dx. So for this one, what is f of x? It's nothing but x into dx plus 1 to 1.5. What is it? 2 minus x. 2 minus x dx. Right? So let us write the integral for x. So for x, the integral is x squared by 2 within the value 0.5 to 1 plus 2x minus x squared by 2 within the value 1 to 1.5. Okay. Let's substitute the values here. 1 by 2 minus 1 by 8. Right? Plus, let's put 1.5 for 3 by 2. This is 3 by 2 now. 3 minus 3 by 2 into 3 by 2 by 2. What will be the value? 9 by 8. Okay, this is 9 by 8 minus, let's put 2 here, plus 1 by 2. Right? So let's write everything minus 1 by minus 2 plus 1 by 2. 1 by 2, 1 by 2 is 1. 3 minus 2 is 1. And then we have this. What value is it? I take minus 1 by 8 common. It's 1 plus 9. 1 plus 1 is 2 minus 10 by 8. I hope I'm right. It's 16 minus 10 by 8. 6 by 8 is 3 by 4. Okay. I'm getting 0.75. Good. So yeah, this probability is always in between 0 and 1. Okay. So we got 0.5, 0.75 as the answer. Is this part clear? If that is clear, let us have a look at the R code. Okay, I hope it is clear and visible to you. Is the screen visible? Can anyone confirm? No. Okay. Now, so integration, I was using it for PDF. So it's a probability distribution for continuous random variables. So for that one, we use integration because we need to find the area under a curve. So that's the reason we use integration in this. Okay. Um, okay. Now, just a moment. I hope this is visible to you. Okay. So for the probability distribution, I'm just showing you guys for some visualization purpose only. You don't have to particularly learn this or something like that. Okay, this is just for you to have an understanding, or if you want to implement in R, you can definitely use this code. Okay, so let us say I have green balls with me. Okay, what are the some different colored balls and also many balls I have. Okay, I just have some green ball. I wanted to take some green balls. So I took a ball out. It can be green or it may not be green. Okay. So let us say I'm taking two balls outside, one after the other. The probability that is zero, like it might be, I may not get one single green ball. I might get one ball at least as green, or I might get both the balls as green. Okay. So I'm just defining the number of green balls. And I'm just defining the probability of drawing zero balls or having just one green ball and two green balls. Okay, these are all just random numbers to you. Okay, let's just run it. So green ball 0, 1, 2, and probability of having the green ball. We have some probability values. So I want to just have a bar plot for it. Is this one visible? I'm just drawing it as a bar plot, having zero greens. I'm having this here. The probability of having zero greens is this. Probability of having at least one green is this, and probability of having two greens is this. Right. So this is something else as plot. Right. Now let us go for some random, continuous random variable. Example here, I'm taking heights of students. Okay. So I'm taking some sequence values starting from 140 till 200 and with a difference of 1. Okay. So I took some height values. Okay, the heights I got from 140 till 200 I got with a difference of 1 here in the environments you can see that. Okay. So to get the probability density function, we use something called as D norm. If you want to read more documentation about D norm, just in the console give a question mark and D norm. Okay, and it will come over here, and you can read it entirely, and you can see what changes you can make now. Okay. So as I was saying, it's a distribution normal distribution function we are using. There are other types as well, D norm, P norm, and Q norm and R norm. You can try each of them by yourself and you can understand what you can figure out the differences. It's easy. Okay. So I'm just using a D norm here. Okay. And I got some heights from the distribution of that heights. Now I want to plot that height. Okay, in the x-axis and in y-axis, I want to show you the probability density. Okay, so let's run this as well. Are you able to see? So on the x-axis, we have the height, and on the y-axis, we have the probability density function. So the probability of having, let us say, we are taking a student, and we want to know what is the probability of that student having the height in between 150 to 180. Then we can point here and 180 here, and we can take the area under this graph using the integrations, right? So far clear? Um, okay, we can go back to the notes again, and we'll come back later to the next part. Okay. The next one we are going to look at is binomial mass function. So in the beginning, in the previous one, we were looking at only different kinds of outputs we are looking at, like we are having so many different kinds of outputs. But here, we are going to look at binomial mass function. In the name itself, which is short, bi means two, nomial means outcome. So I'm having only two outcomes here. So example, tossing a coin. I might have head or a tail. or passing an exam. It's either pass or fail, and things like that. Okay. So well, like you might think, like, okay, it's just a tossing of a coin. I'll toss, I'll get head or tail. That's it. No, why am I making another mass function like this? And you might have that, but it's different. So we are tossing it like so many times, and we want one particular outcome, and that particular outcome happened to be a particular number of times only it happened, and with some probability. Then I want to know the function of it. Okay, so here it is. So if I toss a coin n times, okay, let us say that n is some 50 times. I'll take the coin and toss 50 times. And in k times, I'm getting it as a head. Let us say some k equal to 20. Out of the 50 times, I got 20 times as head with some probability. And the random probability. In the question itself, we will always mention what is the probability. Then, what is the distribution of it? Then the function is equal to n factorial divided by k factorial into n minus k factorial into p power k into 1 minus p power n minus k. So p is the probability here, and n and k values are already given. So as a quick recap to others, if you don't know what this exclamation symbol is, it's called a factorial. So if I'm saying 3 factorial, it's right from 1 onwards, 1 into 2 into up till this number. You have to multiply. You have to keep multiplying it. So that is called as a factorial. If I'm having 5 factorial, then 1, 2, 3, 4, and 5. And multiply it till there. Okay. So that is called as a factorial. The same factorial is used here. Okay. And also, if the n value keeps increasing, so the more number of times you keep increasing uh, the number of times you toss the coin, it is going to look more like a Gaussian distribution. Okay. So in case if I'm having like 5 times I'm getting the output, I might get something like this. Okay. It's not a Gaussian distribution. Gaussian distribution looks something like this. Okay. But in case this is for 5 times. Let us say I'm doing it for 50,000 times. I'm tossing the coin for 50,000 times. Then the probability distribution will look something like this. Almost like a Gaussian distribution. Okay. If you want, you can look up something called as bootstrapping in art. You can see there are many YouTube videos. Uh, so because of the time constraint, I'm not going till that. But in case if there is some time remaining at the end, I'll definitely uh, show bootstrapping as well. Okay. But in case if time is limited, you can have a look at it on the internet. Okay? You guys can try this question with the same formula. Formula is here. Everything is here. You can try this question out by yourself. I can wait. Is it done? Okay, let's go more. We are running short of time. Okay. So let us write the parameters first. So we are tossing it 5 times. So n is equal to what? 5, right? And in the first part, k is equal to 2. Let us take the probability p is equal to half 1 by 2. Like, okay, p is equal to 1 by 2 here, and it's this. Exactly getting 2 heads. So that is f is equal to k is x equal to 2, right? It is equal to n factorial 5 factorial divided by k factorial 2 factorial into n minus k, I minus 2, 3 factorial, p means 1 by 2 power k square into 1 minus 1, 1 minus 1 by 2, n minus k, that is q, right? That is, write it, 5, 4, 3, 2, and 1, 1 and 2, and 1, 2, and 3. That's really well. 1, 2. This one is 1 by 2 power 5. Both are the same, right? 5 to 10 into what is 2 power 5? 32. 10 by 32, yes, 5 by 16. Yeah, 5 by 16 is absolutely right. No, uh, did you want to tell something else? If you got something else, you can just let me know. Okay. So B, at least 4 heads. So that is nothing but f of x equal to 4 plus f of x equal to 5. Okay. Yeah. So these you can automatically do. I don't, it's just keeping in a formula. Or do you want me to do? Because we'll take the answers 3 by 16 for now. I don't usually keep remembering the answers. I just do. Uh 3 by 16 is right. Awesome. Okay. Uh okay, do you guys want to have a look at it in the R code? Sure. Okay, so this is for the binomial mass function. Let us say in this code we are having 5 number of trains, right? So n equal to 5, and the probability that we are taking is 1 by 2, so 0.5. And the total number of successes, here I have given starting from 0 till 5. Like if k equal to 0 to k equal to 5, I wanted to show all of it. Okay, instead if I just want to take the value, okay, let us just do that way. What is our k? K equal to 2, no? For now, we'll do it that way. Okay? N equal to 5, p equal to 0.5, k equal to 2, and the binomial mass. So the binomial mass is calculated using this BBINOM. Okay. Let me just write that here. So the answer for that is 0.3125. Okay. Uh, yeah. So now I want to visualize it as a plot starting from 0 till 5. Like if k equal to 0, and like that is having no head at all, till having all five as heads. Okay. Then I'll calculate. I'm having some set of values and I wanted to plot it. And this is how my plot looks. So these are the probabilities. The highest probabilities are for 2 and 3. Like having two heads and having three heads, we are having the highest probability in that two success rate, right? So when I give this code to you, you guys can manipulate here and there, and you can try out for yourself as well. Okay. Mm, okay. So yeah, we have seen this one. So this binomial mass function is for discrete values. So for discrete outcomes, we are having something. Now we will look at something called as Gaussian or normal distribution. Okay. So these are for continuous values, and I have already shown you how a Gaussian graph looks like. So it is a continuous graph like this. So it's a mountain without a peak, right? So this is the formula this is the function that is used to represent the Gaussian function. Okay. So here mu is nothing but the mean and sigma square is nothing but the variance. Okay. So just reminding, variance is equal to sigma square and standard deviation is root of variance. So that is equal to sigma. Okay. So these are okay. And it is characterized by these two parameters, that is the mean and the standard deviation. And if you will ask why I am telling these as a parameter, I will plot this Gaussian graph and I'll keep varying the mean and the variance. And you will see the difference in between the graph. Okay. So as we change these parameters, the graph also changes. So that is what it means. Okay. So by default, we usually take mean equal to 0 and sigma is equal to 1 for any kind of data. Okay. So we have the formula right at the top for Gaussian. Can you guys calculate the probability density function, that is f of x, of this Gaussian distribution using these values? So x is given, u is nothing but okay, mean, and st is nothing but sigma st. Okay, standard deviation is equal to 3. Can you guys do it? Okay, so we barely have like 20 minutes more. So you can do this by yourself again. It won't take much time. So instead, I would like to share the R code. We'll, we can just have some observations using R. Okay. Okay. So, okay. So just for some example purpose, I'm just taking mean equal to 0 and the standard deviation is equal to 1. And I'm taking a sequence value starting from -5 till +5. Okay. And a division by 0.01, like the gap between every value is point, no, 0.01. Okay. So if I want to find the Gaussian distribution, again, I'll use denorm. Okay. I have stored some values in Gaussian. And now if I plot it, this is how my plot looks like. So here, if you see, the peak is exactly at 0, right? This is all the same. Now let me change the mean value to 5. And I'm keeping the standard deviation the same, x value is the same, everything same. Just I'm running the Gaussian distribution again. Okay. And then let me plot it and see the distribution has changed, right? If I take this as 3 and we'll plot it again. And when I say mean is equal to 5, now I got the peak exactly at 5, right? So while changing mean, the peak point in the graph is shifting by that value, right? So let me bring it back to 0. Let's plot it again. Okay. So we are having it exactly at 0. Now, if I change the standard deviation by let us say 5, okay, then what will happen? What kind of a change did you guys see here? From the before, like when standard deviation is equal to 1, and now when the standard deviation is equal to 5. What difference have you guys seen? Yes, exactly. Amazing. The spread has become larger here, right? So changing this mean and median, the entire distribution is changing. So therefore, we call this mean and the standard deviation as the parameters of this Gaussian distribution, right? Is it clear? Yeah. So let us give the values that we are using. So u equal to 5 and standard deviation is equal to 3 and x is not a significant. We want to see what is the Gaussian value. And this is the f of x value that I'm going to get given the mean equal to 5, standard deviation equal to 3, and x equal to 2. Okay, is it clear? Mm. So like that, you can make your changes and you can manipulate the data and you can check by yourself uh, every here and there. Okay. Let's just tell me one thing. So this chi-square and all of these things have already been covered theoretically during the classes. Do you want me to explain them once and then come back to the R code, or do you want me to continue the R code entirely? I think up to you. Option one is having the theory and then coming to this, and we just have like what 18 minutes remaining. I can continue on the R code. Thank you. I hope it's okay with everybody. I'll just continue. Okay. So then next we are going to the chi-square distribution. So this results when independent variables with standard normal deviation are squared and summed. Okay. So this also has a particular f of x value, just like the Gaussian distribution. Okay. It's a bit different, but yeah. So the parameters for Gaussian distribution, we were having the mean and the standard deviation as the parameters. But here we will have something called as a degree of freedom as the parameter. Okay. So I'm taking a degree of freedom is equal to 5, and then a sequence from starting from 0 to 20. And then for chi-square, we use something called as DCHISQ as the now for the same x values, um, I'll give 15. From from here to here, it's almost closer to 15. Before it was almost closer to 5, right? So only degree of freedom plays an important role in characterizing the kind of a distribution that you are going to have. Okay. So you can try it for 1 degree of freedom, 2 degree of freedom, 10 and 15 as well. So you will have like you will see like different graphs for everything. Okay. So and then in the theory, moments of PDF were also covered. So moments are nothing but certain quantitative measures. So that is related to the shape of the functions of the graph. So we have seen mean and the variance, like we were changing that and the distribution was changing and things like that. So we have something called as first moment and the second moment, third moment and things like that. So the first moment is something called as the expected value. So given something, we get one value, one expected value. Okay, the second moment is nothing but the variance. Okay, and the third moment is squeeness, and fourth moment is something else, and things like that. Okay, so for all of these, you have different outputs and all of that. So I just wanted to tell you, if you want to find the mean, you have to use the function as mean, and for variance, you call the function VAR. So I'm taking the same height data set which we have taken from 140 to 200 or something. So we'll take the mean and we'll take the variance. We want it to print mean, okay, and variance. Okay. So what is mean, what is variance, all of the definitions are already covered in the lectures. Okay. So then we have something called as central tendency. Before I go to that, let me show you some simple statistics. Probably I can just tell it to you. So most of you have heard about population, right? So population is nothing but the set of all possible outcomes for any random experiment. Okay, so now let us say I'm collecting data on diabetes patients. Okay, so I'm having like 20 patients. So these 20 people are my population. Okay, not exactly, but yeah, okay. In the world, how many number of diabetes patients are there? All of them are my population. Okay, they might have different kinds of outcomes in sample set. Now, I can't go and get all the diabetes patients around the world, right? Instead, I will pick some people from different places or from the same place, and and that is called as a sample set. So out of those the maybe like million diabetes people, I'll be taking like 1,000 or 2,000 people for some study. So those 1,000, 2,000 people are my sample set. Okay. And then the other keyword is inference. So from this 1,000, 2,000 people, I will do some study and I'll come to one conclusion. Okay. So this might have been one of the main reasons for the diabetes, I could say. Okay, so that conclusion is called as the inference. So from these sample set that I have with me, what inference I could make. Okay, right? So then we'll come to something called as central tendency. So in central tendency, so it one single value represents the entire distribution. For example, if I give the mean, to calculate the mean, I'm going to take the entire sample set, right? So the entire distribution I'm going to take. For example, this height only, I have the height value starting from 140 to 200, right? So I'm going to take all the 140 to 200 and I'm getting some mean as 170. Okay, so that is one kind. So that is some single value that is representing the entire distribution. Instead, I'm not having the continuous values. I'm having some different values like one, some maybe say your marks out of 10 marks, 10 out of 10, how many marks everyone has scored in one particular subject. Some people might get the same marks over and over again. So let us say out of 20 students, 10 students have got 7 as their marks, and the other one got different values. So mode is the maximum number, like maximum count of one particular value. Okay, so that is the mode. And then you know the median. So in median, usually what you do, if it is a discrete one, you arrange all of them in a descending order or an ascending order, and you take the middle value. So it's okay. So like that, for the central tendency here, I have already shown you mean here. So I haven't given here again. So I just directly wrote mode and I'm taking height, and out of which the maximum one I'm taking, maximum times repeated one. Okay. And okay, for this one, okay, because I'm taking a continuous value like from 140 to 200 with a difference of 1 for the height, I was getting the same values over and over. Okay, but you can change the data and you can try by yourself. Okay. Then I would like to show you some graphical representation. So far we have seen the continuous graph, like the Gaussian distribution graph. We have seen histogram and all of that. No, so I have put all the graphical representations here together. So the first one is the histogram. So yeah, this is how a histogram looks like. Yeah. So how many times a particular number has occurred, that will be on the left side, and on the on the y-axis, and on the x-axis, it is showing me the height. Okay. So that is the histogram. And then we'll have a look at the box plot. So in the box plot, this is the mean. Okay, the mean, and we also have the first quartile, third quartile, all of that. And we also have outliers and all. For box plot, I would suggest you to have a look at it on Google, because it's taking so much time, and we have it's 9 minutes. Okay, and then we have something called as a probability plot. Okay, for that we use a special function called as QQ norm. Okay, so QQ stands for quartiles norm. Okay, we have some sample quartiles and we have some theoretical quartiles, and that is exactly not so relevant to you right now. So this is just for visualization purpose. You don't have to like go through with all of it. Okay, I just wanted to just show you since it has been covered in the theory part. Okay, and then we have something called as a scatter plot. So far, all the first three plots that I have shown, that is taking only one particular value. Like one particular random variable, that is height. So in scatter plot, it is not like that. We need to have two random variables, and both of them are plotted against each other. Okay, I'm taking two different values, height 1 and height 2, and then I'm plotting. So all the plots are like scattered here and there, and hence the name scatter plot. Okay. And then the final topic that we would cover for today is the hypothesis testing. So it is nothing but to we are going to choose a test type. We are going to sorry. It is going to tell us how accurate, like we are going to test something. Like I might have something in my mind. I want to know whether that hypothesis is right or wrong. Okay, hypothesis is my assumption that I have made. So we all have seen for the height data set, we have got the mean as 170. Let us say I did not know that mean and I just assumed the mean to be 180. Okay, so that is my assumption. Mean is equal to 180. And then I wanted to test it. Okay, so uh, just for these number of these heights of these students, I'm thinking the mean height is 180. Am I right or wrong? So that is something we call as hypothesis testing. Something we assume is right or wrong. Okay, so in this case, I'm thinking that the null hypothesis is the mean height of the student is 170. Okay, so if I'm thinking that it is 170, what will be my alternative? Alternative is opposite of the null hypothesis. That is, the mean height of the students is not 170 centimeters. Okay, for this one, we use something called as t-test, two-sided t-test. Okay, and then I'm saying I am here. This 170 here says that I am assuming the mean to be 170 for this data set. What do you think? Okay, and I'll run the t-test. I'll visualize it. So as soon as I ran this t-test, I got this as my output. Okay, so it is telling me the mean of this x is 170. So that means the mean of this height data set is 170, and this p-value here is important. P-value is equal to 1. So the more the p-value, the more accurate my assumption is. Okay. So let us say I am assuming that the uh, height mean height is 180. Okay, and then let me see. If you see, it is telling me no, the mean is 170, and my p-value has reduced from 1 to 4.5 into 10 power minus 5. So my p-value has reduced drastically here, right? So which means that my null hypothesis, that is thinking that the the mean is 180, is completely wrong. Okay, if I give again, let us say I'm giving it as 172, which is closer to the mean value, and then I test it again. So the p-value has reduced, but not drastically. So this is telling me, okay, you are somewhat close to the mean value, but you are wrong. Only if I'm giving the right value here, I'm going to get the p-value is equal to 1. Okay. You can observe the p-values by changing all these mean values here. Okay. I hope you're clear. So the null hypothesis is whatever the mean you are calculating using the data set is equal to the mean that you are assuming. That is null hypothesis. Alternative hypothesis is the opposite of that. Both are not equal. Okay. And yeah, the hypothesis testing and all of that is already there in the lecture. And also there are different types. If you look at this, oh, sorry, I'm supposed to. There is something called as one-sided test and two-sided test. Okay, so you have to give these values here. If I say two-sided, then you can understand it by the graph itself, which is there in the slide. So at the two edges of the, if this is my Gaussian distribution, on this side and this side it will check. And if I'm saying it is on the one side, then for one particular value, it will check only on the one side. Okay. So that is two-sided test and one-sided test. One-sided means lesser or greater. So given one particular value, you have here it is the mean. Okay. You can try that one out as well. Okay. Let me see if I didn't cover anything. Okay. Um, Degree of freedom. Okay. So basically, it is the maximum number of independent values that you have. Okay. And it goes too complicated. Like you need to have a proper example and everything for you to explain. Please explain chi-square. Uh, okay, so basically chi-square is also one kind of distribution. So it is quite clear in the slides if you would like. Okay, I'll just share this screen instead of this. Okay, I'll wrap it up in a minute. So we have some number of independent variables. Okay. So everything is having for all the variables are having different normal distributions. So now what I do is I take all these normal distributions, I square all of them, and I sum all of them. Okay. Uh, you don't have to get too deep into it. So this is also one kind of a PDF. Okay. For the continuous random variables, this is also one kind of PDF. And this is the function. This is the function. And the this tau here is the gamma function, and it is represented using this. So it involves some integration as well. Okay, so we are plotting this particular function using different values. Okay, so here 1 degree of freedom means I'm taking one independent variable with a standard normal distribution. If I'm taking degrees of freedom, means I'm taking two independent variables. Each of them will have its own standard normal distribution. Okay. So I'll take this for normal distribution. I will square them and I'll sum it up. Okay. Okay. Any question? Any more questions? I will add this recording in the in YouTube, and that link will be available in NPTEL portal itself. And then also the drive link is already shared with almost everyone, right? So you can access this notes from the drive link. Okay. Yeah. Thank you, everyone. Again, I'll meet you again on the next Friday. What subspace and everything I have explained in the last lecture. So I would recommend you to go back to the last lecture's recording, and you will find everything there. Okay. Thank you so much. Thank you so much, everyone, for joining, and thank you for being really, really interactive. And thank you, guys. I'll meet you again next week. So I'll end this meeting here. Thank you. You too.